ऑल राइट ऑल राइट ऑल राइट, शुरू करते हैं। आई शुड बी लाइव नाउ। हूँ क्या लाइव? आ गया, ठीक है। कूल। बड़े टाइम बाद आया शाश्वत। चलो शुरू करते हैं डी एंड एफ ब्लॉक से। बाकी कोशिश करूंगा कि आज हो जाए चैप्टर, लेकिन 24 पेजेस का है तो थोड़ा मुश्किल ही है आज के आज कंप्लीट करना। लेट्स स्टार्ट। The D and F block elements, iron, copper, silver, gold, are among the transition elements that have played important roles in development of human civilizations. The inner transition elements, such as thorium, palladium, and uranium, are proving excellent sources of nuclear energy in modern times. The D block of periodic table contains the elements of group 3 to 12, in which the D orbitals are progressively filled in each of the four long periods. The F block consists of elements in which 4f and 5f orbitals are progressively filled. They are placed in a separate panel at the bottom of the periodic table. The name transition metals and inner transition metals are often used to refer the elements of D and F block elements. D and F blocks respectively. There are mainly four series of transition metals: 3D series, Sc to Zn, that is, इसका नाम भूल गया यार, स्कैंडेनियम टू जिंक, एंड फिर 4D ytterbium टू कैडमियम, उसके बाद lanthanum से हैफनियम, lanthanum and hafnium to mercury, and 6D series, which is actinium and the elements from rutherfordium to Cn, copernicium. The two series of inner transition metals, 4F C, that is cerium to lutetium, and 5F thorium to lutetium नहीं LR कुछ और होता है, are known as lanthanoids and actinoids respectively. Originally, the name transition elements were derived from the fact that their chemical properties were transitional between those of S and P block elements. Now, according to IUPAC, transition metals are defined as metals which have incomplete d subshell either in neutral atom or in their ions. Zinc, cadmium, and mercury are of group 12 have full D10 configuration in their ground state as well as their common oxidation states, and hence are not regarded as transition metals. However, being the end members of 3D, 4D, and 5D series, respectively, the chemistry is studied along with the chemistry of transition metals. The presence of partly filled D or F orbitals in their atoms make transition elements different from that of non-transition elements. These, hence, transition elements are the compounds. Transition elements and their compounds are studied separately. However, the usual theory of valence as applicable on non-transition elements can be applied successfully to the transition elements also. Various precious metals such as silver, gold, and platinum are industrially important metals like iron, copper, and titanium. Nahin, like iron, copper, and titanium belong to the transition metal series. In this unit, we shall we shall first deal with electronic configuration, occurrence, and general characteristics of transition elements, with special emphasis on the trends of the properties of first row of 3D elements, along with the preparation and properties of some important compounds. This will be followed by consideration of certain general aspects such as electronic configuration, oxidation states, and chemical reactivity of inner transition metals. The transition metals, D block. Position in periodic table. D block occupies the large middle section of the periodic table, flanked between S and P block in the periodic table. The D orbital is penultimate energy level of receive atoms receive electrons, giving rise to four rows of transition metals, that is 3D, 4D, 5D, and 6D. All these transition elements are shown in table 4.1. Electronic configuration of d block elements. In general, the electronic configuration of outer orbitals of these elements is n-1 d1 to 10, ns1 to 2, except for palladium, where the electronic configuration is 4d10 5s0. The n-1 stands for inert d orbitals, which may have 1 or 10 electrons in the outermost ns orbitals. Ns orbital may have 1 or 2 electrons. However, this generalization has several exceptions because of very little energy difference is in n-1 and ns orbitals. Furthermore, half and completely filled sets of orbitals are relatively more stable. A sequence of this factor is reflected in the electronic configuration of chromium and copper in 3D series. For example, consider the case of chromium, which has 3D5 4s1 configuration instead of 3D4 4s2. The energy gap between the two sets 3D and 4s of the orbitals is small enough to prevent electrons entering the d orbitals. Similarly, in case of copper, the electronic configuration is 3D10 4s1 and not 3D9 4s2. The ground state electronic configuration of the outer orbitals of transition metals is given in table 4.1. Electronic configuration of outer orbitals of transition elements. इनके मासेस हो गए 4s में कितने और 3D में कितने. 4s वाले आप एक्सेप्शन तो कर लेते हैं. हाईलाइट. बाकी हमें ये तो याद ही है. इनकी ट्रिक्स भी क्या ही याद करनी. बोलूँ ऐसे एक बारी. साइंस टीचर वनीता कुमारी माने फीको ने क्यों जान जलाती है. फिर यारी जरा निभाना मौत तक रुकावटें राह में पड़ेंगी आगे कूद. फिर थ्री थर्ड सीरीज दैट इज 5s. ला हफ्ता वरना रे ओसामी इधर पिटाई और होगी. फिर एसी में बैठा रदरफोर्ड डूब गया सागर में. बोहर हंस मत आ, डोसा खा रहा रागा कोने में. ऐसे हमें याद कराया. और अगर हम ये वाले याद करेंगे ना. इसका क्या था. नवाबी एनबी क्यों करे सिया रागा आरजी. आरजी का हो गया. रागा का आर एच होगा ना. आर एच के लिए रागा यूज हुआ है. रागा रुकावटें नहीं. आर एच आर जी होगा कुछ. क्यों करे रागा और पढ़ेंगे आगे पिटाई. चलो रागा था ठीक है. नवाबी क्यों करे रागा रुकावटें. रुकावटें आएगा टीसी के रू और टीसी. हाँ रुकावटें राह में पड़ेंगी आगे पिटाई और. इसकी है नवाबी क्यों करे रागा रुकाव रुकावटें मौत तक पड़ेंगी. नहीं राह में रुकावट. अबे यार मैं भूल गया यार. नवाबी क्यों करे रागा रुकावटें मौत तक रुकावटें राह में पड़ेंगी आगे पिटाई और. ग्रुप वाइज से याद करा था. The electronic configuration of outer orbitals of zinc, cadmium, mercury, and copernicium, था ना? Copernicium are represented by a general formula of n-1 Nd10 ns2. The orbital in their common CD का क्या है? CD का कैडमियम. CD का है भाई. मैं भूल गया. हो रहा. नहीं CD एक्सेप्शन नहीं है ना लेकिन. अच्छा अगर तूने ऐसे याद करा हुआ मैंने तो ये करा होता है. जिंदगी कैडबरी हो गई. ZNH CNH CDH. छोड़ो भी पढ़ते हैं यार बहुत जरूरी. The orbital in these elements are completely filled in ground state as well as in their common oxidation states. Therefore, they are not regarded as transition elements. The d orbitals of transition elements uh, completely filled in. Hmm. D orbitals by transition elements protrude to periphery of an atom more than the other orbitals, that is S and P. Hence, they are more influenced by the surroundings as well as the effect of atoms or molecules surrounding them. In some respects, ions of given D and configuration 1 to 9 have similar magnetic and electronic properties. With with partly filled d orbitals, these elements exhibit certain characteristic properties, such as display of variety of oxidation state, formation of colored ions, and entering into complex formation with variety of ligands. The transition metals and their compounds also exhibit catalytic properties and paramagnetic behavior. All these characteristics have been discussed in detail later in this unit. There are greater similarities in properties of transition elements of horizontal rows in contrast to the non-transition elements. However, some group similarities also exist. We shall first study the general characteristics and the trends in the horizontal rows, particularly 3D, and then consider some group similarities. Onward ground, Scandinavium, and is a transition element zinc is not क्योंकि उसका fully filled होता है completely filled your orbital in ground state क्योंकि उसको एस से एक आया था ताकि उसको completely stable मिले. So can say that it's a transition element क्योंकि उसमें transition करेगा ना states अलग अलग state में जाएगा अपने उसके different states में. We will discuss the properties of elements of first transition series only in the following section. Physical properties. Nearly all the transition elements display typical metallic properties such as high tensile strength, ductility, malleability, high thermal and electrical conductivity, and metallic luster. With the exception of zinc, cadmium, mercury, and manganese, they have one or more typical metallic structures at normal temperature. Lattice structures इनके I don't think इनको याद करने की हमें जरूरत है. The transition metals, with the exception of zinc, cadmium, and mercury, are very hard and have low volatility. Their melting points and boiling points are high. Figure 4.1 depicts the melting point of the transition elements belonging to 3D, 4D, and 5D series. The high melting points of these elements are attributed to the involvement of greater number of electrons from n-1d in addition to the ns electrons in interatomic metallic bonding. In any row of melting points of these metals rise to a maximum at D5 except for anomalous values of manganese and technetium and fall regularly as the atomic number increases. They have high enthalpies of atomization as shown in figure 4.2. ये देख लेंगे. The maxima is about the middle of each of the series, indicates that unpaired electrons per d orbital is particularly favorable for strong interatomic interaction. तो ये वाला मेल्टिंग पॉइंट वाला ग्राफ है जो कि D5 पे मैक्स जाएगा. टेक्नीशियन थोड़ी गड़बड़ गिर गई तो पहले ही गिर जाता है. फिर रूट एंथियम बढ़ता है. मैंगनीज भी गिरा हुआ है. हा हा लोल कितना गंदा है. In general, greater the number of valence electrons, stronger is the bonding. Since the enthalpy of atomization is an important factor in determining the standard electron potential of metals, metals with very high enthalpy of atomization, that is, high boiling point, tend to be noble in their reaction. See later for electrode potential. Another generalization that may be drawn from the figure 4.2 is that the metals of second and third series have greater enthalpies of atomization than the corresponding elements of the first series. This is important factor in accounting to the occurrence of much more frequent metal-metal bonding in the compound of heavy transition metals. तो ये है इनके डेल्टा एच बॉन्ड एंथैल्पी। इनको कंपाउंड के नाम पे तो देने चाहिए थे ना, क्या पता लगेगा कौन सा कहाँ है। तो बैड। Variation in atomic and ionic sizes of transition metals. In general, ions of the same charge in the given series show progressive decrease in the radius with increasing atomic number. This is because the new electron enter a d orbital each time the nuclear charge increases, but by unity. It may be recalled that shielding effect of d electrons is not that effective. Hence, the net electrostatic attraction between the nuclear charge and the outermost electron increases, and the ionic radius decreases. The same trend is observed in the atomic radii of given series. However, the variation within the series is quite small. On increasing the point, on incre- inter- the, An interesting point emerges when atomic size of one series are compared with those of the corresponding elements in another series. The curve in which the corresponding elements in the curves in figure 4.3 show the increase from first 3D to second 4D series of the elements, but the radii of third 5D series are virtually the same as those of the corresponding members of second series. This phenomena is associated with intervention of 4f electrons, which must be filled before 5D series of the element. The filling of 4f before 5D orbital results in regular decreasing in atomic size. This is called lengthenoid contraction, which essentially compensates for the expected increase in the atomic size with increasing atomic number. The net results of lengthened contraction is that second and third D series exhibit similar radii. Example, zirconium is 160 picometer and hafnium is 159 picometer and have very similar physical and chemical properties, much more than the expected one, the basis of usual family relationship. एक बार ये देख लेते हैं रेडियस वाला, ये डिक्रीज ही होता जाएगा और जिंक पे आगे बढ़ जाएगा क्योंकि भर जाएगा, मतलब लास्ट वालों का बढ़ गया वरना नीचे ही जाता जा रहा है। खोल दो, यहाँ पे भी चेंज होना शुरू हो रहा है, यहाँ पे भी क्योंकि स्टेबल कॉन्फ़िगरेशन आए थे ना 9 की D9 की, तभी मतलब D9 स्टेबल नहीं होता लेकिन D9 D10 बन जाता है एक इलेक्ट्रॉन लेके। The factor responsible for lengthened contraction is somewhat similar to the observed in any ordinary transition series and is attributed to similar cause, that is the imperfect shielding of one electron by another in same set of orbitals. However, the shielding of one 4f electron by another is less than that of one d electron by another. And as the nuclear charge increases along the series, there is fairly regular decrease in the size of entire 4Fn series, Fn orbital. The decrease in metallic radius, coupled with increase in atomic mass, results in general increase in the density of the elements. General increase in the density. और ये क्यों होता है? क्योंकि डिक्रीज इन मेटालिक रेडियस एंड इंक्रीज इन एटॉमिक मास, बाहर बढ़ रहा है, वॉल्यूम कम हो रहा है, इस वजह से डेंसिटी बढ़ रही है, दोनों फेवरेबल फैक्टर्स। Thus for titanium Z is equals to 22, to copper Z is equals to 29, the significant increase in density may be noted. तो एक बार ये देख लेते हैं, जो कि वन ऑफ द वेरी इंपॉर्टेंट टेबल्स है क्योंकि डी ब्लॉक के आधे क्वेश्चन यहाँ से ही आते हैं। पेंसिल टूल, ये बढ़ेगा बढ़ेगा, फिर यहाँ पे आई D10 वाली कॉन्फ़िगरेशन, इसलिए घटेगा, फिर से घटेगा, अब D10 से, और D10 कह रहा हूँ, D5 आई, D5 के बाद यहाँ पे D6 आया, फिर बढ़ने लग गया, जैसे D10 आया, D10 4s1, फिर वापस कम हो गया। फिर आयनाइजेशन एंथैल्पी में भी सिमिलर सा ट्रेंड देखना चाहिए, वैसे बढ़ेगा ज़्यादा इसमें नहीं, डायरेक्टली इंक्रीज ही हो रही है, बस यहाँ पे थोड़ा सा चक्कर है, वरना इंक्रीज ही हो रही है। मेटेलिक एंड आयनिक रेडियाई ये डिक्रीज होते जाएंगे। डिक्रीज डिक्रीज यहाँ पे इंक्रीज हो जाएगा क्योंकि D5 आ गया। फिर वहाँ पे डिक्रीज डिक्रीज डिक्रीज, ये ऑलमोस्ट सेम हो गया उल्टा। फिर यहाँ पे इंक्रीज होगा क्योंकि यहाँ पे D10 4s1 आ गया और यहाँ पे D10 आ गया फाइनली, इसलिए बहुत ज्यादा बढ़ जाएगा। फिर है स्टैंडर्ड इलेक्ट्रॉन पोटेंशियल M2 प्लस से M। यहाँ पे सभी का ही नेगेटिव है देन कॉपर, कॉपर का पॉजिटिव है। और फिर M+3 से M+2 आ रहे हैं, जब पहले 2 से 1 है अब 3 से 2 आ रहे हैं। तो उसमें सबसे ज्यादा इसका हो गया मैंगनीज और आयरन। नहीं इनफैक्ट ये क्या कहते थे, कोबाल्ट ना, हाँ कोबाल्ट देन मैंगनीज और आयरन। और उसके बाद सबसे कम हो गया इसका क्रोमियम का। फिर डेंसिटी बढ़ती जा रही है जैसे जैसे आगे जा रही है, जो भी पढ़ा था हमने, क्योंकि एटॉमिक रेडियस उतना नहीं बढ़ रहा जितना ज्यादा एटॉमिक मास बढ़ रहा है। वो को भी याद रहे। There is an increase in ionization enthalpy along each series. The transition elements from left to right due to an increase in nuclear charges, which accompanies the filling of inner d orbitals. Table 4.2 gives the value of first three ionization enthalpies of the first series of transition elements. These values show that successive enthalpies of these elements do not increase as cheaply as in the case of non-transition elements. The variation in ionization enthalpy along a series of transition elements is much less in comparison to variation along period of non-transition elements. The first ionization enthalpy in general increases, but the magnitude of increase is in the second and third enthalpy of the successive is much higher than along the series. ये भी देखोगे एक बार ionization enthalpy का, ये बढ़ रही थी बढ़ रही थी बढ़ रही थी, सबसे कंफ्यूज कितना बढ़ ही रही थी, मतलब ज्यादा गैप से बढ़ रही है, ये डिफरेंस आया। ओके। The irregular trend of the first ionization enthalpy of the metals of 3D series, though by little chemical significance, can be accounted for the consider for nahi, for by considering that the removal of one electron alters the relative energies of 4s and 3D orbitals. You have learned that when d block elements form ions, ns electrons are lost before n-1d. As we move along the period of As we move along the period in 3D series, we see that nuclear charge increases from scandium to zinc, but electrons are added to orbitals of inner subshells, that is 3D orbitals. These 3D electrons shield the 4s electrons from the increasing nuclear charge, somewhat more effectively than the outer shell electrons can shield one another. Therefore, the atomic radii decreases less rapidly. Thus, ionization energies increases only slightly along the 3D series. कितना सारा डाटा है यार इसमें, मतलब एक्सप्लेन करा हुआ ऑल दो, जो कि जरूरी है वरना हम सारा बोल देंगे केमिस्ट्री का एक्सेप्शन है। Thus, ionization energies increases slightly along 3D series. The doubly or more highly charged ions have Dn configuration with no 4s electron. A general trend of increasing values of second ionization enthalpy is expected as the effective nuclear charge increases because of d electrons, because one d electron does not shield another electron from the influence of nuclear charges, because d orbital differ in direction. However, the trend of steady increase in the second and third ionization enthalpy breaks from the formation of Mn plus and Fe3 plus respectively. In both the cases, ions have d5 configuration. Similarly, breaks occur corresponding to the elements in later transition series. The interpretation of variation in ionization enthalpy for an electronic configuration Dn is as follows. सिर्फ एक्सप्लेन करा हुआ है क्या? The three terms responsible for the values of ionization and therapy are attraction of each electron towards the nucleus, repulsion between the electrons, and exchange energy. Exchange energy is responsible for stabilization of energy state. Exchange energy is approximately proportional to the total number of possible pairs of parallel spin in the degenerate orbital. When several electrons occupy a set of degenerate orbitals, the lowest energy state corresponds to the maximum possible extent of single occupation of orbitals and parallel spin, Hund's rule. The loss of energy increases the stability. As stability increases, the ionization becomes more difficult. There is no loss of exchange energy at D6 configuration. Mn plus Mn plus has 3d5 4s1 electronic configuration has and configuration of Cr plus is D5. Therefore, ionization enthalpy of Mn plus is lower than that of Cr plus. In same way, Fe2 plus has DC configuration and Mn2 plus has D5 configuration. Hence, ionization enthalpy of Fe3 Fe, Fe2 plus is lower than the manganese Mn2 plus. In other words, we can say that the third ionization enthalpy of iron is less than that of manganese. The lowest common oxidation state of these metals is plus 2 to form M plus 2 ions from the gaseous atom. The sum of first and second ionization enthalpy is required in addition to the enthalpy of atomization. The dominant term in second dominant term is the second ionization enthalpy. Dominant is the second ionization, which shows unusually high values for chromium and copper, where M plus ions have D5 and D10 configuration respectively. The values of zinc is correspondingly low, as ionization causes the removal of one 4s electron, which results in formation of stable D10 configuration. The trend in third ionization enthalpy is not complicated, complicated by the 4s orbital factor and shows greater difficulty of removing an electron from D5 Mn2 plus and D10 Zn2 plus. In general, the third ionization enthalpies are quite high. All the high values of third ionization enthalpies of copper, nickel, and zinc indicate why it is difficult to obtain oxidation states greater than 2 for these elements. Although ionization enthalpy gives some guidance concerning the relative stabilities of oxidation states, this problem is very complex and no am unable to generalize it. ऑक्सीडेशन शेड शुरू करने से पहले मैं 2 मिनट का ब्रेक ले रहा हूँ अब क्या बोलते हो ऐसा आज मेरा बर्थडे क्लास Okay. Oxidation states. One of the notable features of transition elements is the great variety of oxidation states. These may show in their compound state. These may show in their compound. Table 4.3 lists the common oxidation states of the first row elements. The most common ones are in bold. Titanium का +4, vanadium का 5, chromium का 3 and 6, manganese का +2 and +7, iron का फिर +2 और +3, कोबाल्ट का 2 और 3, निकल का 2, कॉपर का 2 और जिंक का 2। सभी 2 दिखाते हैं एक्सेप्ट दे +2। द एलिमेंट विच गिव, एक मिनट यार, कोई आया रहता है। ऑलराइट, सॉरी, घर पे आ गया था यार। The elements which give the greatest number of oxidation states occur in or near the middle of the series. Manganese, for example, exhibit all the oxidation states from 2 to +2 to +7. The lesser number of oxidation states at the extreme end stems of from either too few electrons to lose or share scandium or titanium, or too many d electrons, hence fewer orbitals available in which to share the electron with others, or higher valence copper and zinc. Thus, early in the series, scandium 2 is virtually unknown, and titanium +4 is more stable than titanium +3 or titanium +2. At the other end, the only oxidation state of zinc is +2. No d electrons are involved. The maximum oxidation state of reasonable stability corresponds in the value of the sum of s and d electrons up to manganese. तो टाइटेनियम का यहाँ पे प्लस क्या, the maximum oxidation state of reasonable stability corresponds to the value of sum of s and d electrons, मतलब कि जितने एस और डी में टोटल सम है उतना मैक्सिमम दिखा सकते हैं ऑल राइट। ठीक है, followed by rather abrupt decrease in the stability of higher oxidation state, so that typical species species to follow are Fe +2 3, copper +2, cobalt +2 and 3, nickel +2, copper 1 and 2, zinc 2. The variability of oxidation states, a characteristic of transition elements, arises from incomplete filling of d orbitals in such a way that their oxidation state differ from each other by unity. Example V2 and 3, V2, 3, 4, 5. This is the contrast in the variability in oxidation state of non-transition elements, where oxidation states normally differ by a unit of 2. An interesting feature in the variability of oxidation states of D block elements is noticed among the group 4 through 10, along with the although in P block the lower oxidation states are favorable by heavier members due to inert pair effect, the opposite is true in the groups of D block. For example, in group 6, molybdenum +6 and wolfram, नहीं क्या होता था W, tungsten, हाँ wolfram ही होता था, wolfram 6 are found to be more stable than chromium 6 and chromium 6. Thus, chromium 6 is formed in the form of dichromate in acidic medium, is strong oxidizing agent. Why? Because they are more stable than oxidizing agent than MOO3 and WO3 are not. Low oxidation states are found when complex compounds have ligand of pi acceptor character in addition to sigma bond. For example, NaCO whole 4 and FeCO whole 5 The oxidation states of nickel and iron is 0. Name a transition element which does not exhibit viral oxidation state. Zinc. Which of the 3D transition elements exhibit largest number of oxidation states? Answer is Mn क्योंकि इसके पास सबसे ज़्यादा इलेक्ट्रॉन होते हैं इधर-उधर करने के लिए. Trends in M plus 2 and M standard electron potentials. Table 4.4 contains thermochemical parameters related to the transformation of solid metal atoms to M2 plus ions in the solution and their standard electron potential. The observed values of E minus electron potentials and those calculated using data of table 4.4 are compared in figure 4.4. The unique behavior of copper having a positive electron potential account for its inability to liberate H2 क्योंकि इसका पॉजिटिव ही होता है इसलिए हाइड्रोजन लिबरेट नहीं कर सकता फ्रॉम एसिड. Only oxidizing acid, nitric acid and hot concentrated sulfuric acid react with copper. The acid being reduced, the high energy transition of copper to Cu2 plus is not balanced by its hydration enthalpy. मतलब हाइड्रेशन एंथैल्पी इतनी होती नहीं कि वो कॉपर को Cu2 प्लस में भेज पाए. इस वजह से हमें स्ट्रॉन्ग हाईली ऑक्सीडाइजिंग एसिड यूज करना पड़ता है. The general form of the trend towards less negative electrode potential values are across the series related to general increase in the sum of first and second ionization enthalpy. It is increasing. It is interesting to note that the values of E minus for magnesium, nickel, zinc are more negative than expected from the trend. मतलब जहाँ पे हम स्टेबिलिटी की तरफ जा रहे हैं वहाँ पे गिरता जा रहा है. ये इसका गिरा, ये गिरा. निकल कहाँ गया? निकल भी. निकल का वरना मतलब ज्यादा होना चाहिए जिस हिसाब से बोल रहे हैं. निकल यहाँ पे होना चाहिए था लेकिन वो यहाँ पे नहीं है. Why Cr plus 2 reducing and Mn plus 3 is oxidizing when both have D4 configuration. Cr plus 2 is reducing as its configuration changes from D4 to D3. The later having half-filled T2G level. On the other hand, the change of Mn plus 3 to Mn plus 2 results in half-filled D5 configuration, which has extra stability. Okay, it's a pretty good point. The electrode potential values of copper is positive. What is possible reason for this? Consider high atomization energy and low hydration energy. Answer is इन्होंने से एक तरह से. Thermochemical data in kilojoules for first rock transition element. The stability of half-filled D subshell in manganese plus 2 and completely filled D10 configuration of Zn plus 2 are related to their electrode potential values, where electrode potential value of nickel is related to highest negative hydration energy. निकल की हाईएस्ट नेगेटिव हाइड्रेशन एनर्जी होती है, एंथैल्पी सॉरी. Trends in M3 plus and M2 plus. An examination of electrode potential values show that the varying trends show the varying trends. The low value of scandium reflects the stability of scandium plus 3, which has a noble gas configuration. The highest value of zinc is due to the removal of an electron from stable D10 configuration of Zn2 plus. The comparatively high value of manganese show that Mn plus 2 is particularly stable, whereas comparatively low value of iron shows the extra stability of D5, Fe3 plus, that is D5 configuration. The comparatively low value of vanadium is related to the stability of V plus 2 half-filled T2G level. मतलब पहले हम मेनली डी ऑर्बिटल कंपेयर करते हैं, उसके बाद वो भी उससे भी कम में आ गए तो हम T2G EG इस तरफ से जाते हैं इनको फिल करने में, इनका कंपैरिजन करने में. हाफ फिल्ड होगा तो ज्यादा स्टेबल होगा. कूल. Trends in the stability of higher oxidation states. Table 4.5 shows the stable halides of 3D series of transition metals. The highest oxidation numbers are achieved in TiX4 tetrahalides, vanadium F5, And chromium F6, the +7 state of manganese, is not represented in simple halides, but MnO3F is known. Beyond Mn, no metal has a trihalide except FeX3 and COF3. यार पांच में से दो तो करती ही हैं. The ability of fluorine to stabilize the highest oxidation state is due to either higher lattice energy, as in case of COF3, or higher bond enthalpy terms from higher covalent compounds. जिनकी ज्यादा bond enthalpy होगी वो ज्यादा covalent compound बनाएंगे. Example VF5 and CrF6. Chromium या cobalt. ठीक है, ये cobalt fluoride. Although V plus 5 is represented only by VF5, the other halides, however, undergo hydrolysis and give oxohalides, FeOX3. Another feature of fluorides is their instability and low oxidation states. Example VX2. X can be Cl, Br and I. एक बार देख लेते हैं. टाइटेनियम +4 3 और 2 बनाता है. वेनेडियम +5 +4 +3 और +2 +4 ये क्यों बोल रहा हूँ मैं. वेनेडियम X4 X5 X4 X3 और X2 बनाता है. X5 X4 X3 X2 कंफ्यूज हो रहा हूँ. क्रोमियम F6 से लेकर 2 तक बनाता है. मैंगनीज 2 से 4 तक. आयरन 2 3, आयरन और कोबाल्ट दोनों 2 और 3. निकल 2, कॉपर 2 एंड कॉपर 1 और Zn X2. अच्छा, यहाँ पे जो पावर में दिया हुआ है ना, जैसे यहाँ पे और यहाँ पे, हाँ, इनमें X1 का मतलब ब्रोमीन है. ब्रोमीन नहीं, फ्लोरीन और ब्रोमीन. फ्लोरीन से ब्रोमीन है क्या? हाँ, फ्लोरीन से ब्रोमीन मतलब FCl और Br. लिख देते यार, एरो की जगह जगह पे Cl आया था. फिर जहाँ पे सिर्फ और सिर्फ X है वहाँ पे F से लेके I तक ये जितने भी हैं बाकी के मेजर. यहाँ पे तो दिया ही VF5 है. यहाँ पे भी दोनों F5 और F6 दिए हैं. ये X है सिंपल, ये वाला भी X है, यहाँ पे भी X है, यहाँ पे भी X है. बस यहाँ दो जगहों पे और X2 और X3 हैं. और ये जो X2 वाला है ऊपर 2 की पावर वाला, वो फ्लोरीन और क्लोरीन हो सकते हैं. और 3 वाला Cl और I हो सकते हैं. Cl और I और Cl और I. ठीक है. And same applies to CuX. On the other hand, all Cu2 halides are known except of iodide. In this case, Cu2 plus oxidizes I minus to I plus, I2 sorry. Cu2 plus 4I minus will give Cu2 I2 plus I2. However, many copper compounds are unstable in aqueous solution and undergo disproportionation. Cu plus, Cu2 plus और Cu में चला जाएगा 0. The stability of Cu2 plus rather than Cu plus is due to much more negative delta H hydration of Cu2 plus aqueous than Cu plus, which is more than compensates for the second ionization enthalpy of copper. Okay. The ability of oxygen to stabilize the highest oxidation state is demonstrated in the oxides. The highest oxidation number in the oxides coincides with the group number and is attained in Sc2O3 to Mn2O7. Beyond group 7, no higher oxides of iron above Fe2O3 are known. Although ferrates, FeO4 minus are formed in alkaline media, but they readily decompose to Fe2O3 and O2. Besides the oxides of बड़ा सारा डाटा है इस पैरा में, सारे ऑक्साइड्स के बारे में डिस्कस कर दिया. Besides the oxides, oxocation stabilizes V5 as VO2 plus, V4 as VO2 plus, and titanium 4 as TiO2 plus. The ability of oxygen to stabilize these high oxidation states exceeds that of fluorine. Thus, the highest manganese fluoride in MnF4 is MnF4, whereas highest oxide is Mn2O7. दैट इज +7 ऑक्सीडेशन स्टेट, फ्लोरीन के साथ सिर्फ +4 में. The ability of oxygen to form multiple bonds to metal explains its superiority. In covalent oxides Mn2 plus O7, where each Mn is tetrahedrally surrounded by O, including an MnO-Mn bond. MnO-Mn bond. मतलब कि स्ट्रक्चर हो जाएगा ऐसा, M bond M Mn है, बस ऐसे समझ लेना. फिर यहाँ पे डबल बॉन्ड, इधर डबल बॉन्ड और इधर डबल बॉन्ड, सिमिलर इधर. हाँ, और ये डबल बॉन्ड के साथ सारे O है. कूल. हाँ. The tetrahedral MO4N minus ions are known for V5Cr6, manganese 5, manganese 6 and manganese 7. यहाँ पे सारे ऑक्साइड्स दिए हुए हैं, इनको एक बार देख लेते हैं. स्टार वाल देख लेते हैं. ये वाले मिक्स ऑक्साइड, हाईलाइटर, ये मिक्स ऑक्साइड है तीनों. Mn3O4, Fe3O4 and CO3O4. Here, how would you account for the increasing oxidizing power of VO2 plus, Cr2O7 2 minus and MnO4 minus? This is नहीं, VO2 plus is less than Cr2O7 2 minus is less than MnO4 minus. इनके oxidizing power. This is due to the increasing stability of lower species to which they are reduced. Okay, how would you account for irregular variation in ionization enthalpy? तो पढ़ लिया यार ऊपर बहुत बार. केमिकल रिएक्टिविटी ऑलमोस्ट हाफ वे थ्रू, शायद 2 सिटिंग्स ही लगेंगे इसकी, तो बहुत मुश्किल हो जाएगा फिर आगे कंप्लीट करना. चलो करेंगे. Transition metals vary widely in their chemical reactivity. Many of them are sufficiently electropositive to dissolve mineral acid, although a few are noble, that is, they are unaffected by single acid. एक बार मैं देख रहा हूँ कि मतलब कहाँ तक आज का टारगेट रख सकते हैं, क्योंकि 1 घंटा होने वाला है, 10 मिनट रह गए बस. कॉलोड आयंस, ऐसा करते हैं, ये कॉम्प्लेक्स वाले पार्ट तक कर लेते हैं आज. कैटालिटिक प्रॉपर्टीज से कल कर लेंगे. ये 1, 2 और 3 पेज कर लेते हैं अभी. हाँ. The metals of first series, with exception of copper, are relatively more reactive and are oxidized by 1 molar H plus through actual rate at which these metals react with oxidizing agents like hydrogen ion. Though the actual rate at which these metals react with the oxidizing agent like H plus ion is sometimes slow. For example, titanium and vanadium, in practice, are passive to dilute non-oxidizing acids at room temperature. The E0 values of Mn2 plus or M indicate the decreasing tendency to form divalent cations across the series. Decreasing tendency to form divalent cations. This general trend towards less negative electrode potential values is related to the increase in some of the first and second ionization enthalpy. It is interesting to note that E0 values for Mn, Ni and Zn are more negative than expected from the general trend, whereas the stability of half-filled D subshell D5 in D5 in Mn plus 2 and completely filled D subshell in zinc are related to their electrode potential value. For nickel, E0 value is related to highest negative enthalpy of hydration. वही जो है वो डब्बे के नीचे लिखा हुआ था सारा, उसको एक्सपेंड करके लिख दिया. An examination of E0 values of redox couple M3 plus and M2 plus tables, table 4.2 shows that Mn plus 3 and CO plus 3 ions are the strongest oxidizing agent in aqueous solution. The ions Titanium plus 2, vanadium plus 2, and chromium plus 2 are strong reducing agents and will liberate hydrogen from dilute acid. Example: 2Cr2 plus 2H plus gives 2Cr3 plus H2. Okay, magnetic properties. ये पढ़ लो एक मिनट, ये भूल गया. For the first row of transition elements, E note values are this. Explain the irregularity in the above trend. यहाँ पे +5 आ जाती है कॉन्फ़िगरेशन, फिर इधर डेल्टा एच हाइड्रेशन ज़्यादा होता है इस वजह से. बाकी जिंक का इन्होंने दिया हुआ नहीं हुआ, उसकी भी स्टेबल कॉन्फ़िगरेशन हो जाती है D10. ये है ना इरेगुलर तो यहाँ पे रहने से इंक्रीज हो गया, फिर वापस डिक्रीज डिक्रीज डिक्रीज, ये इंक्रीज हो गया. पढ़ लेता हूँ एक बार. Values are not regular, which can be explained from the irregular variation of ionization enthalpy of Hi delta H1I plus delta H2I, and also the sublimation enthalpies, which are relatively much less for manganese and vanadium. दोनों की तो सेम होगी वो. Why is E naught values of Mn plus 3 plus 2 couple much more positive than that of Cr plus 3 plus 2 and or Fe plus 3 plus 2? Explain. Much larger third ionization enthalpy of manganese, where the required change is D5 to D4, is mainly responsible for this. This explains why plus 3 shade of Mn is of little importance. +3 है, हम D4 में चले जाएंगे, लेकिन +3 से +2 जाएंगे तो हम D5 में जाएंगे, जो कि स्टेबल होगा. और आयरन और क्रोमियम का पुट्ठा ही है, उसमें T2G, इसमें T2G स्टेबल हो जाएगा, इसमें D5 स्टेबल हो जाएगा, हाफ T2G. Why is the highest oxidation state of metal exhibited by oxides and not chlorides? ऑक्साइड स्टेबिलिटी भी प्रोवाइड करते हैं उनकी इलेक्ट्रोनेगेटिव का, तो उनके साथ साथ मतलब कंपाउंड को संभाल पाते हैं. वेट पर पढ़ लो यार, +2 क्या था मैं भूल गया. क्या ही था. The ability of oxygen to form multiple bonds to the metal explain its superiority. ठीक है, चलो. Magnetic properties. When magnetic field is applied to a substance, mainly two types of magnetic behavior are observed: diamagnetism and paramagnetism. Paramagnetic substances are repelled by applied field, while the diamagnetic are repelled and paramagnetic are attracted. Substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism. Many of the transition ions are paramagnetic. Paramagnetism arises from the presence of unpaired electrons, each such electron having magnetic moment associated with its spin angular momentum and orbital angular momentum. For the compounds of first series of transition metals, the contribution of orbital angular for the compounds of first series of transition element, the contribution of orbital angular momentum is effectively quenched and hence is of no significance. For these, the magnetic moment is determined by the number of unpaired electrons and is calculated by using spin-only formula. That is, mu is equal to n into n plus 2 ka root, where n is the number of unpaired electrons and mu is magnetic moment in units Bohr magneton. A single unpaired electron has magnetic moment of 1.73 Bohr magneton. Magnetic moment increases with increasing number of unpaired electrons. Thus, the observed magnetic moments give a useful indication about the number of unpaired electrons present in the atom or molecule. The magnetic moment calculated from the spin-only formula and those derived experimentally are of some ions of first row elements are given below. तो पहले लिखिए 0 0, तो ऑलमोस्ट सेम ही है. इनको तो क्या ही पढ़ना, क्योंकि हम तो मेनली यही वाली यूज करेंगे ना, अगर पेपर में हमें करनी भी होगी बताने क्या अनपेड चेक करने के लिए. इसको क्यों पढ़ना अभी. ठीक है। फॉर्मेशन ऊपर क्वेश्चन था ना, कैलकुलेट द मैग्नेटिक मोमेंट, क्या कैलकुलेट करनी, इसका भी सेम है। व्हेन एन इलेक्ट्रॉन when an electron from lower energy d orbital is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. The frequency generally lies in the visible region. The color observed corresponds to the complementary color of the light absorbed. The frequency of the light absorbed is determined by the nature of ligand. In aqueous solution, where water molecules are ligand, the colors of ions are observed and listed in table 4.8. A few colored solutions of D elements are illustrated in figure in this figure. लेफ्ट टू राइट ऐसे में ही दिया होगा, ये V+4 है, फिर ये V+3, फिर मैंगनीज, देन आयरन +3। तो बढ़िया है, ऐसे मतलब देखेंगे तो अच्छे से याद होगा। कोबाल्ट का ब्रिक रेड, और दिख नहीं रहा मेरा। फिर निकल का ग्रीन, पता नहीं कौन सा रेड होता था कोबाल्ट का, लिखा होगा ना यहाँ पे। वो ब्लू पिंक, ब्लू कहाँ है इसमें? हाँ, ये निकल नियॉन पे लिख दिया मैंने। फिर ये कॉपर, कॉपर तो ब्लू होता है तो याद रहेगा। वेनेडियम और निकल ऑलमोस्ट सेम है, बस वेनेडियम थोड़ा ज्यादा डार्क। ये टेबल एक बार देख लेंगे। 0 वाले कलरलेस, 1 वाले पर्पल और ब्लू की रेंज में रहेंगे, 2 वाले ग्रीन, 3 वाले वायोलेट, तो 4 वाला भी एक वायोलेट है। फिर ऐसे याद था ना, मतलब Mn+2 का पिंक था, कोबाल्ट का पिंक था, तो फिर नहीं, आयरन और निकल ग्रीन थे +2 वाले, Mn पिंक है यहाँ पे लिखा हुआ। फिर कुकर ब्लू कलर का, ये CO+3 और Cr+2 ब्लू कलर के। अरे ब्लू कोमा पिंक होना चाहिए यहाँ पे, ये स्लैश होना चाहिए, ऐसे होगा। फिर कॉपर का ब्लू होता है और जिंक का कलरलेस होता है। टाइटेनियम इज पर्पल, वेनेडियम ब्लू, वेनेडियम+3 इज ग्रीन, वेनेडियम+2 इज वायलेट। मतलब हम यहाँ पे ब्लू से वायलेट में आ गए, ब्लू ग्रीन वायलेट, बड़ा रैंडम आ गया। Formation of complex compounds. Complex compounds are those in which metal ions bind a number of anions or neutral molecules, giving complex species with characteristic properties. Few examples are FeCN plus FeCN6 3 minus, FeCN6 4 minus, CuNH3 4 2 plus, PtCl4 2 minus. The chemistry of complex compounds is dealt in detail in Unit 5. The transition metals form a large number of complex compounds. This is due to the comparatively smaller size of metal ions, their high ionic charges, and availability of d orbitals to form bond formation. चलो भी यहाँ तक पढ़ लिया, 16 से 24 तक आ गए, 9 पेजेस रह गए, इनको कल पढ़ लेंगे। I guess it's pretty cool. तो मिलते हैं अब कल की स्ट्रीम में, 1 घंटे की होगी आज भी। कल भी देखता हूँ मैं 1 बजे के आसपास ही स्ट्रीम करने आऊँगा। ऑलराइट, बाय बाय।